Welcome to The Explainer. Today, we're going to pull back the curtain on something that happens inside your computer billions of times a second. It's a story about a huge speed gap, a sort of invisible crisis, and the absolutely brilliant system that was designed to fix it.
So here's the plan. We'll start by digging into this massive problem. Then we'll introduce its really clever solution. We'll see how that solution actually works under the hood, explore what happens when things get complicated with multiple cores, and then wrap it all up with why this stuff really matters to you as a programmer. All right, let's dive right in. You see, inside every computer, there's this constant, invisible tug-of-war going on. On one side, you've got your processor, which wants to just tear through calculations at lightning speed, and on the other, you've got your main memory, which, well, just can't keep up. 200. Just let that number sink in. That's roughly how many clock cycles a super-fast modern CPU can waste, just sitting there, twiddling its thumbs, waiting for a piece of data to arrive from your main memory, your RAM. You know, in a world where a CPU is doing billions of things a second, 200 cycles is an absolute eternity. It's kind of like asking an Olympic sprinter to stop for a full minute mid-race just to get a sip of water. It's a total performance killer. But there is a way around this, and the difference is just staggering. Instead of that 200-cycle penalty, the CPU can grab that same data from a special, high-speed chunk of memory called a cache. And how long does that take? Maybe 15 cycles. We're talking more than 10 times faster. This isn't just a small tweak, it's the secret weapon that makes modern computing possible.
Yeah, and the author of the paper we're looking at today, Ulrich Drepper, he just nails it with this quote. He basically says that the real bottleneck for most software today isn't the CPU speed anymore. It's getting the data to the CPU. This whole problem has a name, the memory wall. It's the fundamental challenge that hardware engineers have been fighting for decades, and it's the entire reason caches even exist.
Okay, so this brings up a pretty obvious question, right? If the main memory is so slow, why don't we just make all of it super fast? Well, like with so many things in engineering, it all comes down to a trade-off. And here it is. It's all about speed versus cost. The super fast stuff, called SRAM, is incredibly expensive to make, and it uses a lot more power. The slower memory, DRAM, is way, way cheaper, which is why you can have gigs and gigs of it in your laptop. So you can have fast and small, or you can have slow and big. You just can't have it all.
And this is where the CPU cache comes in as this really elegant compromise. It's basically a small, exclusive holding area right next to the CPU, and it keeps copies of data that the CPU is likely to need again really soon. The best way to think about it is like a chef's spice rack. A chef doesn't run to the massive supermarket every time they need a pinch of salt. No way. They keep the most common ingredients right there, within arm's reach. The cache is that spice rack for your CPU.
But this spice rack? It isn't just one simple shelf. Oh no, it's a very sophisticated, highly organized system. And to really get why it's so powerful, we need to peel back the layers and see how it's actually built, right inside the processor. You see, caches are set up in this hierarchy of levels. When the CPU needs some data, the first place it looks is the tiny, insanely fast Level 1 cache. If the data isn't there, that's called a cache miss. It then checks the bigger, slightly slower Level 2 cache, and then the even bigger Level 3. Only if it strikes out on all cache levels does it have to pay that massive 200-cycle penalty and go all the way out to main memory.
Now here's where it gets even smarter. The system is not moving data around 1 byte at a time. That would be wildly inefficient. Instead, it moves data in these 64-byte chunks called cache lines. And this is based on a brilliant bet, a principle called spatial locality. The hardware assumes that if you need one piece of data from memory, you're probably going to need its neighbors pretty soon too. So just in case, it grabs the whole neighborhood at once.
So, this whole system works beautifully for a single CPU core. But let's be real, pretty much every device you own has multiple cores these days. So what happens when 2 or 4 or 8 cores all need to access the same data at the same time?
This creates a huge challenge. I mean, think about it. If core number 1 grabs a piece of data into its private cache and changes it, how does core number 2 know that its copy of that same data is now totally out of date? It's stale. Without some kind of system to manage this, you'd have complete chaos. It's a problem called cache coherency. So how do they solve this? With a really complex set of rules, a communication protocol, often called messy. Basically, every single cache line gets tagged with a state, like shared or invalid. Now, before a core is allowed to write to a piece of shared data, it first has to broadcast a request for ownership message across the chip, telling all the other cores, hey, back off, invalidate your copies, because I'm about to change this. All of this chatter creates a lot of overhead.
And all that communication leads to this really nasty performance trap called false sharing. This is what happens when two cores are working on completely separate variables. They aren't actually sharing anything. But just by bad luck, those two variables happen to live on the same 64-byte cache line. The hardware has no idea. All it sees is that the line was modified, so it kicks off that whole expensive process of invalidating and passing ownership back and forth, slowing everything down, even though the cores weren't really interfering with each other at all.
So this brings us to the big finale, the most important question of all. Why does any of this deep hardware stuff matter to you as a developer? Well, it's because understanding this hidden system, from the memory wall all the way to false sharing, is the absolute key to writing software that works with the hardware, instead of fighting against it.
So what can you do? Well, the great news is it's often about really simple habits. Things like just looping through an array in order from start to finish, instead of jumping around randomly. When you do that, you're playing right into the cache's hands. You're taking full advantage of that spatial locality we talked about, and you're helping the hardware predict what you're going to need next. Keeping your data structures small and tight also helps, because it means you aren't wasting that precious cache space on junk you're never even going to use.
When you really get down to it, the CPU cache isn't just a component. It's a masterclass in how you solve physical limitations with incredibly clever design. It's a powerful reminder that sometimes the biggest performance wins don't come from writing more complicated code, but from understanding the elegant, hidden systems that are silently, tirelessly making everything work.